So good day again, class. Our discussion today would be on adsorption. So this is the third of the four topics under part 2 of the unit operations review for chemical engineering review class. Now, adsorption as a process is not very the same as absorption, or shall I say they are really very different in terms of the method in which the component is being separated from the mixture that it is contained. Now the process here is a component coming from a fluid which is in the form of a gas or liquid is adsorbed on the surface of the adsorbent. Adsorbed meaning it's just on the surface, it is not whatsoever linked in the matrix of the solid adsorbent, so it's only on the surface. Adsorbent is usually placed on a fixed bed. It could also be in a fluidized bed, but often the system is the solids that needs to adhere the component from a particular fluid is placed in a fixed bed. Now the fluid is passed through the bed where solid particles adsorb component from the fluid, or that could be from the liquid or the gas. Now, saturated adsorbent, the adsorbent that has been fully utilized or whose surface is already 100% covered by these components that were transferred, could be regenerated. So they can be regenerated and used again in subsequent operations. Now, what are common applications of the process of adsorption? So we have liquid phase adsorption in the case of the separation of paraffins from aromatics, and another one is the separation of fructose from glucose if they are in a mixture together. Now in the case of gas phase adsorption, so we have the removal of H2S or CS2 and other odorous compounds from air, and this is really very common. And in here we can also have one application, which is the removal of organic solvents of paints in air. That is organic solvents that have already mixed, solvent gases that have already mixed with air in the production of paints. Now adsorbents are material that adsorb the component from a particular fluid, so they can be either artificial or naturally occurring with a highly developed surface which readily adsorbs matter from solutions surrounding the adsorbent bed. Now, in terms of the adsorptive property of an adsorbent, it depends on its composition, chemical composition, its physical surface condition, its degree of porosity, and its surface area. So, 4 factors actually are affecting the manner in which a particular component gets adsorbed on a particular solid adsorbent. Now, adsorbents must have, so this is a requirement for all adsorbents, they must have high abrasion resistance, they should have high thermal stability, and small pore diameters. So thermal stability meaning if there are changes in the temperature, their adsorbency property or their property to adsorb components on its surface should not be affected. And it's a given that they should have small pore diameter so that the components that needs to be transferred need not be linked in its matrix already or in the pore structure of your adsorbent. And each adsorbent should have a distinct pore structure, or it should have its unique pore structure. Now, most industrial adsorbents fall into one of these 3 classes that you are seeing on your screen. So one is or are those oxygen containing compounds. So they are typically hydrophilic and polar, including materials such as silica gels, and zeolites. Now, second one are carbon-based compounds. So if oxygen-containing compounds are water-loving, so this one is not so loving with water. So are typically hydrophobic and they are non-polar, including materials such as activated carbon and graphite. So the carbon-based compounds are actually the most abundant available locally. In terms of their availability, we won't have any problem. Now, as for polymer-based compounds, they can either be rather polar or non-polar, and they have porous polymer matrix. So these polymer-based compounds are of course synthetic. They are made. Now, what are examples of adsorbents? So I think you have already in mind what are common examples of adsorbent, and on top of the list is activated carbon. So it's highly absorbent, and it's powder in form, made of carbon, made by thermal decomposition of wood, coconut shell, palm shells, oil, husk, and sawdust. So they can be derived from these sources. I'm referring to activated carbon, or AC. Now, the surface areas of this range from 300 to 1,200 square meter per gram. Average pore diameter of 10 to 60 microns for their openings. Now, as to their applications, we have groundwater purification, dechlorination of processed water, water purification for swimming pools, and even the polishing of treated effluent. So activated carbon actually is the most readily used adsorbent because it's not expensive and its supply is, shall we say, not limited. Now, the second is the silica gel. So it's a granular and porous form of silicon dioxide made by acid treatment of sodium silicate solution to produce a gelatinous precipitate that is washed, then hydrated. So surface areas range from 600 to 800 square meter per gram and have average pore diameters of 20 to 50 angstrom. So there should be angstrom here. Now, as to applications, it's used for drying of processed air, adsorption of heavy hydrocarbons from natural gas, and it is even used as a drying agent, as you can see in packagings wherein this silica gel is included in the packing inside. Now, we have also activated alumina. So this is a highly porous material manufactured from hydrated aluminum oxide by heating to drive off the water. So surface area ranges from 20 to 500 square meter per gram with average pore diameter of 20 to 140 angstrom. So applications, so they can be used as catalyst and they could be used as fluoride adsorbent. Now, molecular cellulites. These are microporous aluminosilicate minerals that form an open crystal lattice containing precisely uniform pores. So different cellulites have pore sizes from 3 to 10 angstrom. So the smallest so far in terms of diameter. Now, application of these molecular cellulites are varied. So you have drying of processed air is on top of the list, CO2 removal from natural gas, carbon monoxide removal from reforming gas, air separation, catalytic cracking, and catalytic synthesis and reforming. So it's just, I think these are just one of the or few of the many applications of molecular cellulites. Now, the synthetic polymers or resins, so from the term synthetic, so they are made. So made by polymerizing two major types of monomers, which are aromatics and acrylics. So coming from the aromatics and the acrylic combination. So we have the synthetic polymers or resins. Now, application include the use to decolorize sugar solution. So I think this is very common if you want to whiten sugar, and the recovery of antibiotics from plant extracts and even proteins. So it's one of its application, or a few of its applications are stated here in terms of synthetic polymers or resins. Now, let's talk about the concentration pattern in fixed beds. Now, or shall we say, let's look into what's happening in the case of fixed bed adsorption. So the concentration in the fluid here and solid phase changes with time as well as position in the bed. So of course, in view of some of the components of our fluid being adsorbed on the surface of the absorbent, we of course have this thinking and understanding that the concentration of the adsorbent and at the same time the fluid phase that contains the solute is going to change with respect to time and with respect to position inside the fixed bed. Now, most of the mass transfer occur near the inlet. This is a given. It's because the adsorbent in the inlet are yet not exhausted at the very first time that it enters the bed. I'm referring to the fluid. So since it is in the inlet that the greatest uptake of the component solute from the fluid is observed, this particular pattern repeats itself once the solid adsorbent in the bed are already, shall we say, saturated or exhausted. So meaning once the solid in the inlet part of your bed is already saturated or exhausted, it would be the next part which will be following the same pattern of adsorption of the component from the fluid. So after some time, it's discussed in here, most of the mass transfer occur farther from the inlet, since the solid near the inlet is already said to be saturated. Now, the region where most of the change in the concentration occurs is referred to as the mass transfer zone. I think it is best explained in here. So the region in which there is greatest increase in the concentration of the solute being adsorbed in the adsorbent is the mass transfer zone. So this is one mass transfer zone. So there is a decrease in the value of C over CO because C refers to concentration of the fluid over initial concentration. It is observed to decrease because as time moves on in the process of adsorption, the component from the original fluid gets adsorbed on the bed, so the C decreases. So that is why you see here a decrease. Now after some time, this solid here in this part is already saturated and exhausted, so there won't be any uptake anymore of the solute here by the adsorbent. It will happen on the next batch of solid and then the next and next, carrying or following the same pattern of decrease in the ratio value of C and CO. Now this one, this particular horizontal axis represents the height of the adsorption bed if it is vertical in orientation, or the length of the adsorption bed if it is horizontal. Now there is this thing what we call breaking point or breakthrough point associated with adsorption. So what is this? This is the maximum concentration that can be discarded, which is on the range of 0.01 to 0.05 of feed concentration. So meaning at the breakpoint class, after this, your fluid that was processed in this fixed bed absorption, let's say equipment, will only contain around 1% to 5% of the solute, meaning only 1 or 5% of the original amount of the solute that it has. So then it could be discarded. So this particular breaking point is the starting point wherein we observe this particular concentration of your fluid. So meaning your bed is already exhausted and it cannot anymore absorb the remaining amount of solute in the fluid. So it's ready to be discarded. The maximum concentration that can be discarded. So that starts on the break point. Although until time t sub 6 in the illustration, there would still be an uptake. There will be an increase in the amount of solute in the fluid because some of the solute that already adhered on your adsorbent surface re-emerge. So the term that was used is re-emerge, meaning it loosened up from the surface because the surface is already saturated and it mixed with the remaining in your solution. So that is why after this particular time, which is the breakthrough point time or the break point time, the adsorption process has to be stopped because you will only get to, or the bed will only get to loosen some of the solute that already had adsorbed on the surface of the adsorbent. it will loosen and it will re-emerge, and it will combine with the remaining solute in the fluid that were not adsorbed. So as breakthrough continues, I think I explained this already, the concentration of the adsorbate in the effluent increases gradually up to the point D. And after such time, it won't anymore increase because, as I said, this is only the remaining amount of solute that will remain unabsorbed in your given fluid. Now, let's look into adsorption principle. So, since the width of the mass transfer zone does not change, the effect of the moderate changes in feed concentration on the breakthrough point can be determined. So, adsorbers are scaled up from a laboratory test in a small diameter bed, and the large unit is designed for the same particle size of adsorbent and superficial velocity that was used in the lab. Then the scaling will be based now on the amount of the true fluid that will be processed in the plant. Okay, so small scale first so that it could be scaled up. Now, the scale-up principles is that, take note of this, the amount of the unused solid or the length of the unused bed does not change with the total bed length. So, it's just like something like ratio and proportion. So, if you have like a length of the bed around 5% of the entire length of the bed, which is unused for a particular adsorbing process or adsorption process, then whatever is the length of the bed that you're going to design later on, the same amount of the entire height or length will be remaining unused. Meaning, if there's 5% in the lab scale, it would also be 5% later on in the actual factory or in the industry. So you just have to look at the upscaling here as a ratio and proportion thing. Now, I have here a formula, since adsorption problem are mostly, even if you're going to read your unit operations books, are graphical in terms of their approach. There are problems that could be directly utilized in determining the breakpoint time. And the breakpoint time here is given as the T asterisk, which is the time when C over CO is equal to 50%. So, meaning your original concentration of the fluid was already decreased to half of it. So, meaning the 50% was already adsorbed. So, that's the T asterisk time. How long would that take? That would be T asterisk time. So, determining the break point requires you to determine the T asterisk. The LUB is the length of the unused bed, where L is the total length of the bed. Now, this could be translated, the L and the H here. You can change this to, this one is L and this one is LUB. LB rather, because this one is the used length of the bed. This is a formula taken from John Couples. So the length of the bed used up to breakpoint, so of your entire length of the bed, how much of your packed adsorbent length in the bed was used up to breakpoint. That would be equal to the ratio of the TU and the T sub T multiplied to the total bed length. So the T sub U and the T sub T is the fraction of the total bed capacity utilized up to breaking point. The fraction of the total bed capacity utilized up to the break point. So meaning in terms of the capacity of the bed, if it's just 70% used up, then this T over T sub U over T sub T rather is just 70. Then you multiply that to the total bed length or the total bed height to give you the length of the bed that was used for breakpoint. So which is actually common sense in this case, this formula. Now, when we speak of batch adsorption, this is often used to adsorb solutes from liquid solutions when the quantity treated, of course, are in small amounts. So, consists of contacting an adsorbent with another material for a given period of time. And the amount of solute adsorbed per unit amount of adsorbent is given by this particular formula. Here, K is a constant and this is determined experimentally. So this is what I mean when I said that most of the adsorption problem in the book are graphical because the determination of the K is graphical. N is a constant which is also determined experimentally. So it is actually comparable to the rate law in kinetics. You determine the order of the reaction and you determine the rate constant. Both are determined empirically through a series of experiments. So it's the same thing here. And C is the concentration in the solution, or the concentration of your solution in terms of the solute that needs to be adsorbed. As to the material balance that we can use, there is a material balance equation in Giancouplis, and McCabe has also one for adsorption process. This one, I think, if I'm not mistaken, was taken from Giancouplis. I'm not sure, I have not checked if Colson has his different material balance, but actually you need not memorize as long as you understand what you are balancing. So in this equation, you are actually on the left side accounting for the amount of the solute initial, and this is the amount of solute that is already in the adsorbent and in the remaining solution. So you look at it, your S is the volume of the feed solution. So this is the volume of the feed solution. M is the amount of the adsorbent. C sub F is the initial feed concentration, this one. C is the final concentration. QF is the initial concentration of the solute, and Q is the final equilibrium value. So it sums up actually the initial amount to be equal to the final amount. The final amount that accounts for the solute in the adsorbent and the solute remaining in solution. So this is the last two terms here. The initial amount is the solute in the feed and the solute in your adsorbent if there is any. So you account for those solutes. So total amount initially should be equal to total amount final after the process has already gone or finished. Now in fixed bed absorption, this is widely used method for adsorption of solutes from liquids or gases employing a fixed bed of granular particles. So fluid to be treated usually passes down through the packed bed at a constant flow rate. So the fluid passes down through the packed bed at a constant flow rate, and mass transfer resistances are important in the fixed bed process. Now though the process is really in unsteady state. Now what are then the process variables and adsorption cycles that you need to know regarding adsorption? So we have cyclic batch system, or we have the continuous flow. So I have in a few minutes ago mentioned about batch adsorption. So it's under this one, the cyclic batch, and we have one that is continuous. So the adsorption fixed bed in this case is alternately saturated. So once it's saturated, it is being regenerated. After regeneration, it's again being used. So that's why it's called cyclic batch. Use, regenerate, something like that. But for a continuous flow system, this involves a continuous flow of the adsorbent countercurrent to a flow of feed. So the feed continues to enter the bed to be processed in the bed, while at the same time there is also continuous removal of the adsorbent from the bed. So it's a continuous flow system. Now, if it's a cyclic batch system, since it's like use the bed, regenerate the adsorbent, use the bed, regenerate the absorbent, something like that. So it's a cycle. There are 4 basic methods commonly used in fixed bed. So generally, the 4 methods operate with 2 or 3 fixed beds in parallel. So if we're using cyclic bed, the cyclic batch bed system has 2 or 3 fixed beds in parallel. So regeneration in the first bed is done using any of the following methods. So the regeneration is done using the things that will be discussed in the successive slides. So take note, this is for the use and regeneration of the adsorbent. The adsorbate is withdrawn by batch also. once the bed is to be regenerated, the adsorbate is withdrawn. So let's see. Now, one of the mentions here, the regeneration could be any of the four. So this is one, the temperature swing cycle. So also called the thermal swing cycle. The spent adsorption bed is regenerated by heating it with embedded stream coils or with a hot purge gas stream to remove the adsorbate. So the process of regenerating the adsorbent is through the use of heating. So the purpose is to purge it with hot gas to remove the remaining adsorbate. The time for regeneration in this case is generally a few hours. Okay, so that's one way of regenerating in the cyclic batch system. The other one is the pressure swing cycle. So the bed here is desorbed by reducing the pressure of the essentially constant temperature and then purging the bed at this low pressure with a small fraction of the product stream. So a small fraction of the adsorbate that was removed through the cyclic batch process is being used when the bed is in the process of desorption, meaning the remaining adsorbate in the adsorbent is being removed by purging it at reduced pressure or low pressure at constant temperature, which will allow the remaining adsorbate adsorbed on the adsorbent to be removed. So the thing that you are to remember with pressure swing cycle is reduced pressure at constant temperature procedure. So this process for gases, so take note, it's for gases, uses a very short cycle time, though the cycle time was not specified. In the inert purge gas stripping cycle, the adsorbate is removed by passing a non-absorbing or inert gas through the bed. The regeneration cycle times are usually only a few minutes. So in this case, we're not increasing the temperature, we're not reducing the pressure at constant temperature, but rather we're using a non-absorbing or inert gas. It is passed through the bed, that way it can take with it the remaining adsorbate on your adsorbent. It's non-absorbing, so meaning it is not going to be absorbed in your adsorbent matrix. That's the inert purge gas stripping cycle. Now, what about the displacement purge cycle? So the temperature and pressure are kept essentially constant. So this time, both temperature and pressure is constant, but a gas or liquid is used that is absorbed more strongly than the adsorbate and displaces the adsorbate. So take note, if the inert purge gas stripping cycle will use an inert gas that won't get absorbed in the matrix of your adsorbent, this one at constant temperature and pressure uses a gas that will get absorbed. The purpose is for that gas to displace the adsorbate in your adsorbent. So since it gets absorbed, it will displace the adsorbent on the surface. Now cycle times here are only a few minutes, so even shorter than the temperature or thermal cycle. Stream stripping is often used in regeneration of solvent recovery system or regenerating of solvent recovery systems using activated carbon as absorbent, or rather adsorbent. So this should be adsorbent. Now, what are this? This is common in adsorption, the topic called absorption, what we call the adsorption isotherms. So these are curves relating the equilibrium concentration. Take note, equilibrium concentration of the solute, meaning no mass transfer anymore will occur at this point on the surface of the adsorbent Q to the concentration of the solute in the liquid C, with which it is in contact. So the concentration of the solute on the surface of the adsorbent Q to the concentration of the solute in the liquid C. So meaning the remaining solute in the fluid that was processed. So we take the concentration of the two and have it plotted. So C kilogram adsorbate per cubic meter of fluid in the bed. this one is Q, kilogram adsorbate per kilogram of adsorbent. And there are 3, so you see 2 curves and a line in this plotting of these 2 concentrations. Let's look at the equations representing the line. So the one that is linear, is referred to as the linear isotherm. So this is the slope of the line, and this is the relationship between C and Q, linear, with no y-intercept. For the Freund-Luch isotherm, so you have the Kc raised to n, so comparable to the rate law. You have the exponent here, which is the order of the reaction, and you have the K here, which is the rate constant. So the Freund-Luch isotherm is this one, the curved one. Okay? And the last, of course, is the Langmuir, which is the one that is strongly favored. Why? Because it's the one that is accurately getting the values. So here, the Langmuir isotherm gives the relationship between the K, the C, the Q, and the Q max. So you have 4 things that could be seen in this equation. But in terms of relationship, you are actually giving the relationship between the concentration and the concentration of the adsorbate in the adsorbent. The concentration rather in the solution, I missed to finish that one, and the concentration of the adsorbate in the adsorbent. So this is the equation. It's more detailed than the first 2, and as such, this one gives you a more accurate result. So everything here are defined. So Q max is the maximum adsorption capacity for forming a single layer only. N is a constant. C is the concentration of the adsorbate in the solution. K is the adsorption constant, and Q is the concentration of the adsorbate in the adsorbent. So that's your Langmuir isotherms. Now, what are the different adsorption equipments? So we have the fixed bed absorbers, the ones commonly used. This is stationary with filter streams. Important properties include pressure drop and life expectancy of the adsorbent, and very predictable in these types of systems. So the life of the absorbent is very predictable. So meaning how long will a particular adsorbent will be used. So you can readily determine using this particular equipment. It's simple, relatively inexpensive, and is most commonly used in processing scheme. Most common processing scheme is a pair of adsorbents. So meaning this is usually used in tandem with another. So 2 fixed bed absorbers. As one is getting regenerated, the other one is being used. When the second one is being regenerated, the first one is being used. That's the purpose. Then the number of adsorbents here are selected based on the optimization of overall process operation and cost benefits. Applications ranging from large industrial operations to removing harmful VOCs or the volatile organic carbons to small consumer uses as filters and gas masks. So consumer uses for filters and gas masks is also using the principle of fixed bed adsorbers. So these are examples of fixed bed adsorbers. We have the fluidized bed. Now this one utilizes a more complex moving fluidized adsorbent to filter the system. So this time your adsorbent solids are not fixed. They are moving together with the fluid that is to be processed. So achieved by inducing a stream velocity high enough to suspend the adsorbent particles. So in the process of flowing the fluid together with the adsorbent, there has to be enough velocity, that way your adsorbent, that is your solids, remain suspended in the fluid as they move. Higher energy cost compared to fixed bed adsorbers. Okay, this will be highly energy intensive in terms of use, and behavior of fluidized beds is much harder to predict in terms of how long will it last in terms of the life of the adsorbent. Require a larger chamber Now, this usually is implemented in high volume industrial application. So it's a given actually that when you're using something that is batch, the thing that you will have to process is only small in terms of amount. But if it's large amount, this has to be converted to continuous. So that is the case of the fluidized bed adsorbent. So since you're going to process a bigger amount, you're going to of course incur a lot of cost. One cost here is of course the energy use in making sure that the velocity of the fluid should be enough to make the solid suspended as they flow together. Now this is your fluidized bed absorbers. We have also moving bed adsorbent. So the bed is moving. So adsorbent can be kept Adsorbent can be kept to a minimum, and heat transfer is better compared to fixed bed adsorber. So more complex, more expensive than fixed beds, and in here we have attrition of adsorbent particles. And that would be the end for adsorption class. I will go to the next liquid-liquid extraction on our next recorded lecture video.